Today is our pleasure to have Ken Hing. He was born in Hong Kong and lived there for 20 years until he joined the MIT. And now he's a fourth-year PhD student at the MIT Physics, focusing on gravitational wave data analysis and astrophysics, as well as exploring the science potential of next-generation gravitational wave detectors. So please go ahead, Ken.
Okay, so can anyone see the screen okay?
Yeah. Good.
Okay. All right. So first of all, thanks for inviting me to give a colloquium talk in the BHI here. Today I'm talking about the constraints on the ultralight bosons. Okay, sorry, one moment. I need to move the panel a bit. Okay, so sorry about that. The constraints on the ultralight bosons with black hole speed measurements from the gravitational waves. So this work, the method of this work has been pressed on PLD, and the main results has been under review. And this work has been collaborating with my supervisor and also two collaborators, Otto Hendrikseller and also John Ely. So first of all, I will introduce what's ultralight bosons. So, okay. So ultralight bosons are really any boson with a very light mass. So by very light, we are really talking about 10 to the minus 33 eV as well as 10 to the minus 33 eV. Or up to 10 to the minus 5 eV. So these bosons can be either scalar, vector, or tensor particles. So why are we interested in these very light bosons? It's because there are a few very important theoretical implications. So for example, possibly the first invention of this notion is on the QCD axion, which solves the strong CP problem. And the second one is about the cosmological problems about dark matter. So there's a class of dark matter called Fussy dark matter or wave dark matter, which try to solve some of the cosmological problems that cannot be resolved by the lambda CDM model. There's the standard cold dark matter model. And the third class is, of course, the string theory. And in string theory, there's a lot of predictions of these very light particles that solve some of the theoretical problems in the string theory aspect. So again, I'm not an expert in string theory, but so that's what I actually know. So for the bosons, they can have self-interaction, which will lead to a lot of rich phenomenology. So in this talk, I will just skip the self-interaction. So just take the boson as very weakly interacting each other. And there are some existing constraints because these bosons, are not very are not new particles that is proposed a few years ago. So they actually proposed like decades ago. So in this plot, I showed the current constraint, well, actually not quite current. So you can see that it's from the particle data group review in 2014, but this plot is for the top purpose is the curious plot. So that's why I showed this plot 5 years ago. So the x-axis is the mass of the axion, and then for QCD axion, there is like a special relation between the mass of the axion and also the interaction strength of the axion. So on top of that, that would be the interaction strength of the axion, or some people call it decay constant. So there are actually quite a lot of experiments that try to put constraints on the mass of the axion, right? So through different channels. So there are like astronomical observations like Goblet cluster, Weisdorf, and so. And also there are some particle experiments, for example, ADMX. And there are lots of more particle experiments that try to explore the mass of axion. So this plot doesn't really include all of the constraints. So, but notice that in most of these experiments, they can only reach down to 10 to the minus 7 eV. And the question is, how do we actually reach the lower end of the mass spectrum of the axion that I just mentioned in previous slide, like down to minus 33 eV, right? 10 to minus 33 eV. So we make use of a phenomenology called a black hole atom, which then can help us to probe the really light ultralight boson or axion below 10 to the minus 11 eV. And okay, so what is a black hole atom, or what is like a gravitational hydrogen, to be more precise? So it turns out that the ultralight boson can interact with a highly spinning black hole through a process called superradiance, and then form a so-called gravitational hydrogen or gravitational atom. So here is a simple fact sheet that lay out the similarity between the gravitational hydrogen and also the ordinary hydrogen that we observe with the electron and also the proton. So in our case, the curved black hole or the spinning black hole acts like a nucleus, and then the ultralight boson will form a cloud structure around the spinning black hole, and forming a cloud structure that is analog to the electron cloud in the hydrogen atom. So I'll highlight a few things here. So first of all, we can define a so-called fine structure constant, which is also similar to the fine structure constant in the quantum mechanics. But in our case, the constant is really the ratio between the black hole radius, which is characterized by the mass of the black hole, versus the wavelength of the ultralight boson particles, because in this limit, we treat it as a classical scalar field. So, and the wavelength is inversely proportional to the mass, to the rest mass of the boson. And the clouds have similar spherical harmonic states as the ordinary hydrogen atom. So there's a set of quantum numbers of the cloud state structure of the boson's cloud. So we can characterize with the NRM. So also you can also specify energy levels, things like that. So because this is a classical system, it's not really a quantum system. So it turns out there are some significant difference, which also leads to other phenomenology that is very different from an ordinary atom. So for example, the boson cloud is only stable for m that is larger than 0. So the m here is azimuthal quantum numbers of the cloud state. And the cloud itself, because it's like a gravitational system, so the cloud itself actually is dissipative, meaning that it will emit continuous gravitational wave, which is another huge subject in terms of gravitational wave detections. But in our talk, we can discuss after the talk, because this is really interesting. But in our talk, we don't make use of the cloud emission itself. So here is the schematic picture. And actually, I should also mention that Asimina Afanitaki in Perimeter Institute actually put this idea together, the gravitational atom. So this is really an amazing work. And of course, Asimina is an expert in the theoretical field. So yeah. Now I talk about the gravitational hydrogen. So what actually drives the system, the formation of this system? So it's through a process called superradiance. So here I will just briefly go over the important physical mechanism. So we can of course discuss the physics in more deep extent afterwards. But in my talk, I would like to highlight the results rather than the underlying physics. So I'll just briefly introduce the process here. So what is superradiance? Superradiance made use of basically starts with the very famous Penrose process, which says, that if you scatter a wave towards the ergosphere of a curved black hole, so for the ergosphere of a spinning black hole or curved black hole is really a special region that even for a stationary observer, it would be dragged along the spinning direction of the spinning black hole. it turns out that if you scatter a wave towards the ergosphere, the outcoming wave would be amplified, and then you can actually extract some energy from the black hole through the scattering process. So this is really a very simple description of Penrose process. Of course, there are some more physics in it. But now you can put one step further and ask, and this is actually done by Press and Tukowski 2 years after. So if you put a mirror around the black hole, and what will happen? Now, you can think of a scattering wave that has been amplified after scattering out of the ergosphere. Now you have a mirror, so the scattered wave will reflect back and then goes into the ergosphere region again, and then it will be further amplified, and then that means you have a runaway instability, which creates a so-called black hole bomb, because now the wave is amplified for many times because there's a mirror cavity there. Now, of course, like in nature, we don't really expect where is a mirror, right? So then we ask, in nature, is there something that is similar to a mirror? And it turns out that really after a few years, and he actually solved the Klein-Gordon equation and the curved black hole metric, and turns out the mass of the boson, if there's like a massive particle around the black hole, the mass term acts like a mirror. And that means there will be a spontaneous growth of the boson field, as long as some criteria satisfied. And I will explain the criteria in the next slide. And that means there will be a spontaneous extraction of the black hole's energy and momentum until this criteria is no longer satisfied. So that means a black hole was spin down to a so-called critical spin because because we have this superradiance criteria. So what is this inequality? It really says the wave frequency of the boson field has to be slower than some integer multiples of the black hole angular frequency at the horizon, which is characterized by the black hole mass and spin. So in this plot, the x-axis is the black hole mass, the y-axis is the dimensionless black hole spin running from 0 to 1. And there are three colorful curves. So each curve corresponds to the critical spin curves. So meaning that above this curve, superradiance can happen for a particular mode. So for example, blue curve is the first mode, the orange curve is the second mode, the green curve is the third mode of the cloud state. Now above that, superradiance can happen for that mode. And then below that, superradiance cannot happen for that mode. So that really means that if the boson really exists, so we should not expect any black hole boson system would lie on the gray area with in this plot. So meaning that we should not expect, so for example, a boson mass at 10 to minus 12 eV, we should not expect there's a black hole that is with very extremal spin, say for 20 solar mass or so. So that means the black hole mass and spin measurements can, especially the spin measurements, can actually constrain the boson, because if you see a very highly spinning black hole, then that means this boson cannot exist. Otherwise, the boson should have spun down the black hole, and we should not observe that. Now, of course, the superradiance process that spins down the black hole it does not happen instantaneously, right? Because these are like classical gravitational system. So the time scale is quite important. And in the next few slides, I will go through the time scale hierarchy here. So superradiance growth needs to saturate within the edge of the black hole so that we can observe a significant spin down effect. Now, so what is the typical time scale for superradiance to happen? So it turns out that for one e-folding time scale, so the child here, is inversely proportional to some power of the alpha G. So again, the alpha G, you can take it as the coupling constant in the boson black hole system. So for smaller alpha G, so you can think of the effective potential is weaker and it's very hard to amplify the wave. So another consequence is that the clouds of higher modes would grow slower. It's really you can think of like in the usual hydrogen atom, is you need to input some energy to excite a ground state electron to a higher mode. So in the gravitational atom is also similar. So although it's a spontaneous process, it needs to take longer time to excite the higher modes. So for example, we have a black hole that is with 30 solar mass with boson mass that is 10 to the minus 12 eV. And for the first mode, it's very quick. So we are talking about year timescale, which is shorter than most of the astrophysical timescale that we have. For the second mode, the timescale will be much longer. Now we're talking about 1,000 year. And then for higher modes, for third mode, it will be about mega year. So that means we need to take into account to the superradiance timescale in order to estimate the realistic exclusion regions, right? Because we know the black holes should have a finite amount of lifetime. So there's one more complication is that to observe a significant black hole spin down, you need more than one e-folding, and it turns out you need about 180 e-folding. That means in order to observe a spin down, the black hole age has to be longer than the 180 e-folding timescale. That means that in the same black hole mass and spin parameter space plot, so the exclusion region was shrink from the weak coupling side because again, for weak coupling, the superradiance timescale is longer. So if you have an finite amount of time, then you don't really observe the superradiance spin down from the weak coupling side. So for example here, the more realistic exclusion regions with two black hole age, say, let's start with black hole age that is about 10 mega year, that would be the smaller, a smaller gray region that is bounded by the black solar curve. And if the black hole age is longer, so the lifetime is longer, let's say, which is about the age of the universe, then the exclusion region would be slightly larger. Now, as an example, say we have a 45 solar mass black hole initially at some spin around 0.8, so it can spin down to the second mode of the critical spin of the second mode within 1,000 years. And if the age of the black hole is just 10 mega year, it cannot spin down further because from the second mode critical spin to the third mode critical spin, it takes about 100 mega years. So unless the black hole is really, really old, as old as the age of the universe, then it may further spin down to the third mode. And all in all, that would mean like the astrophysical timescale is really relevant in our estimate of the boson mass constraint. So that means we have to compare the superradiance timescale to the astrophysical timescale. So for our system, because I work in LIGO and we talk about binary black holes, so we need to think about what is the typical time delay between the black hole formation to the binary black hole mergers, right? So it turns out that assuming you have initially a stellar binaries, and then black holes form when the binaries evolve, and then it merge at the end. So the time delay between the whole process is dominated by the gravitational wave dissipation after the black holes are formed. So any stellar process we are talking about like within a 1 mega year or even faster, like maybe a couple of 100 kilo year. And the gravitational wave dissipation with some conservative estimate of the initial orbital separation, it takes are typically 10 mega a year. So like in this illustrative plot, so I show from the binary formation. So let's say we have for the smaller black hole, which has a very high spin, so that superradiance condition is allowed. And then within a very short time, it will spin down to the critical spin of the first mode, and there's a cloud around it. So the first mode of the cloud, and then the cloud would dissipate. And then if the in-spiral time is shorter than if the in-spiral time is longer than the superradiance timescale of the second mode, then the second mode can be excited, and then the black hole will be further spun down to the second mode critical spin. And depending whether the third mode superradiance timescale is shorter or longer than the in-spiral timescale, and in our case is longer, so that means the black hole would have the second mode critical spin at the merger. So this is the chi-m here is the final quantity that we observe in LIGO during the merger phase. So that means we need to find the highest mode such that the black hole age is larger than 180 superradiance timescale of the highest mode. Now, of course, we don't just observe one binary black hole, right? And we can observe a lot of black holes. So what that means is that we can actually look for more signature in the black hole population. So for example, this is again the black hole mass spin plot. And let's say initially, like we have the black hole spins at formation that is uniform, and also uniform in the black hole mass, just for an illustration. Now, let's say you have a boson that is 10 to the minus 12 eV, and say the black hole age is typically like 10 mega a year or so. And then we can calculate what is the critical spin curve, and above that, that would be like the exclusion region of the governed by this boson due to the boson superradiance spin down. So that means all the points in the gray area would eventually map to this critical spin curve. So you can see the points that originally in the gray area would cluster around this critical spin curve after the superradiance spin down that is illustrated by the last plot that I showed before. So this is the spin at the merger chi-m that we can actually measure. And this is the population signature here. Now you may wonder, so okay, so now we have a boson, and then we know that there's the coupling constant has to be roughly 0.1, so that the superradiance is effective in order to observe a spin down. So what is the parameter space for LIGO and also for other observatory, right? So for example, for stellar mass black holes, say 1 to 100 solar mass that is observable by LIGO, Figo, or Kagra observatory. So the boson mass that we can constrain is quite narrow comparing to the particle physics experiment, but it's not bad. So we are talking about 2 order of magnitude, so 10 to the minus 11 to 10 to the minus 13 eV. If you have a heavier black holes, then the boson mass parameter space will be lighter. Say, like intermediate mass black hole would be 10 to the minus 13 to 10 to the minus 17. And then for LISA, which can observe supermassive black hole, or even for Event Horizon Telescope that directly image the black hole, then we can further constrain a lighter boson. So here is a plot that is a wonderful plot by Richard Brittle a few years ago, so which really shows the whole spectrum of the boson mass and also black hole mass and their correspondence in this plot. So I'm not going through the details in this plot, but really shows astrophysical black holes can really cover a very wide range of the boson masses that properly cannot be achieved by the particle experiment. And another thing is that precise measurements of the black hole spin is necessary because now, well, this plot is few years ago, so the LIGO black hole spin, which are the black, which are the red points with a very huge error bar, so it's pretty much, it can be anything. So, but for EM black holes, say the X-ray binaries, they will usually put a higher better constraint, but of course, there will be also model systematics behind. So we have to keep this in mind. And again, because this is a PHI colloquium, so I have to mention this important result. So, so we have the direct imaging of the M87 from the Event Horizon Telescope, and actually, Dafür DSO and Danton 2 years ago actually used this result to put constraint on a very light, around 10 to the minus 21 or 10 to the minus 20 boson mass. This will be constrained. So that means the boson cannot really exist within this mass, very tiny mass range. Now, so that would be exciting that if Event Horizon Telescope can measure the spin for more supermassive black hole, then we can extend the constraints nearby. So that will be also very exciting result. Anyway, back to the LIGO binary black hole spin measurements. So how do we actually measure the spin from the binary black hole? So we know the binary black hole emits gravitational wave, and gravitational wave waveform encodes the mass and the masses and the spins of the two black holes in the binary. Now, there is a quantity called effective spin that is a mass-weighted projection along the angular orbital momentum vector. This is the one that we actually measure very well. But then, because for superradiant spin down, we are interested in spin magnitudes instead of the reduced effective spin, right? So it turns out that the spin magnitude is very poorly measured, and it's just because the gravitational waveform, if you calculate it, so the spin magnitude can be degenerated with other parameters, say mass ratio or things like that. So that means the prior on the spin magnitude at the formation of black hole is very crucial, because that will affect the probability that a black hole can be spun down through superradiance process. Because if the formation spin is preferentially close to zero, then the superradiance condition is not even satisfied. So even a boson exists, then we cannot observe any spin down effect from superradiance process. And somewhat unfortunately, so we only have 6 out of 45 binary black holes within the so-called O3A or we call the GWTC, the binary black hole catalog, in the second catalog. So only 6 of them have okay precision of the spin magnitude measurement. So this is the spin disk plot that usually show in the catalog paper. So from the origin, you draw a vector from the disk, and the spin for each pixel, if the color is darker, then that means at that pixel, the spin magnitude and the tilt angles of the spin vector is more likely to be there. So for example, possibly the most significant spins, so the GW190412 and also GW190517. So these are really the two systems that we can constrain the spin vectors in a more precisely than the other system. Okay, so I'll talk about this spin measurements of binary black holes. So, and I also talk about, there's some population signatures in the binary in the black hole spin measurements. Then let's put some expectation first. So let's say now we have a bunch of black hole spin measurements. So is it easier to put constraints or is it easier to measure the boson mass? So there are two different expectations. So the first thing is that it's always easier to put constraints because, as again, like in this plot, so the exclusion region of the black hole's mass and spin, you pretty much just need one black hole that is lying inside the gray area, the exclusion region, so that it violates the super-radiant spin time process, right? So that means we just need a very few precise mass spin measurements of the black hole lying on this exclusion regions to reject the boson existence. So for example, if you have you have a big dot here, it can pretty much reject the boson at 10 to the minus 12 eV. Now it's actually harder to actually prove the existence of the bosons because not just that we need a missing fraction of the high spins of the black holes, but we also need a lot of measurements to actually map out this critical spin curve. Now this is essential. So they are circled in red. So we need to measure the clustering within this critical spin curve because the missing fraction of the high spin may be just some astrophysical coincidence, right? Or maybe there's some stellar process that produce a very small spin of the black holes. So in order to actually measure the boson mass, it's essential to have this clustering around the critical spin so that we can disentangle from the astrophysical process that produce favorably as small spin measurements. Okay, so we have two expectations. And now let's say if the current data, so the GWTC2 catalog, can actually provide some insights to actually put constraints or measure the boson mass. Now, the first thing we can do is really, the simplest thing is to calculate exclusion region. So in this plot, I show the exclusion region for 10 to the minus 12 eV and also 2 times 10 to the minus 13 eV. And we just overlay the spin mass and spin measurements on top of the exclusion region and say, okay, can we eyeball something eyeball some insight out of it? And it turns out that even with this rough estimate, so we can see that the GW 1904-12 and also the 1905-17. So these two black hole mass and spins measurements have a very large overlap with the exclusion region of the boson mass at the 2 times 10 to the minus 13 eV. Then we can also see that there is some consistency that these two spin measurement that may follow the track of the 10 to the minus 12 eV. So let's put a more quantitative question. So the first one is whether these two systems are enough for some small constraints and whether a boson around 10 to the minus 12 eV really exists. And to answer these questions, so we need to go through some statistical technicalities. So I'll try to be brief here. So if you have more questions, I can answer after the talk. So let's say we start with a spin distribution at the formation. So we characterize with a beta distribution, and so that the fraction of the black holes that can undergo superradiance is characterized by the alpha and beta parameters. So I should apologize that it's a bad choice of the parameterization calling alpha and beta. So don't mix this alpha with the coupling constant alpha G. So those are two different parameters. And here the plot really shows the shape of the beta distribution. So it usually recovers some simple distributions, a uniform linear increase, linear decrease, and it can also reproduce a peak structure that favors high spin, depending on the actual values of the alpha and beta. And now let's say we have a boson so that we can calculate what is the probability distribution of the spin at merger given a boson mass and also the alpha and beta shape parameters. And then we go through a standard Bayesian hierarchical inference, so that we not only we fix the alpha and beta, but we also sample the shape parameters alpha and beta as well as the boson mass to calculate the posterior density of these three parameters. So here's the master formula. I'm not going through the details, but the inputs are really the individual mesh spin and mass and spin measurements from the gravitational wave detection, and also we need a model that's model the superradiance effects in terms of a population level. Okay, so all in all, so we try to not assume a formation spin distribution, but we try to infer simultaneously the boson mass and also the properties of the statistical properties of the spin, the black hole spin at formation. So this is crucial here. Now, so this is the last slide of the technicality. So we can also do a model comparison. So as I said, right, so how do we distinguish like apparently small spin distribution to be whether they are due to the boson superradiance or just because of the astrophysical distribution, the astrophysical process that favors small spin. So we have two hypotheses. So if the boson exists, then the formation spin will be reduced because of superradiance. And for astrophysical hypothesis, assuming there are no other astrophysical process, and that alters the spins, so the formation spin would be remains unchanged, and the formation spin would be the same as the merger spin that observed in LIGO. And then we can calculate a so-called Bayes factor between two hypotheses. So you can take it as a Bayesian generalization of the maximum likelihood ratio test. So I'm not going through the math there. But usually a convention is that the larger than 100 is strongly favor the boson hypothesis, and smaller than 0.01 is favor the boson hypothesis. Now back to the two questions. So these two events enough for some small constraints? The answer is yes. And whether the boson whether there's a boson around 10 to the minus 12 eV, the answer is uncertain because of the I will explain this in the next few slides. So after running through the Bayesian hierarchical inference so we find that there is only 0.01% posterior probability support for very tiny boson mass range, 1.3 to 2.7 times 10 to the minus 13 EV. So to show that, so in this plot, the x-axis is the log 10 of the boson mass, or you can read the scale on top. So the y-axis is the posterior probability density in log scale, I should emphasize. And then there are three curves. So I will first draw your attention to the blue curve first. So for the blue curve is making use of all data. And then we do the inference, and then we try to measure what is the possible boson mass. So in the gray area, we see a significant gap around the range that I marked in this slide. So this range only has a 0.01 posterior probability support. So that gives us the constraints that the boson cannot exist everywhere in this gray area. Now, again, so whether the 1905-17 and 1904-12 are necessary to drive constraints, to answer that, so we do two more inference by excluding the 1905-17 and also both 1905-17 and 1904-12. So those are the two curves, the purple and also orange curve. So you can see the gap there disappears. So it's really these two, it's really these two events that drives the constraints in this tiny gray area. Okay, so if you have a sharp eye, and you can see there's a tiny peak here around the 10 to the minus 12 eV. And so if you may wonder, okay, if it's real or not, right? Because as I mentioned, the data may, so we may be fooled by the data that it can be coming from an astrophysically small spin, or we start with a high spin that has a superradiant spin down effect. So to quantify this peak, we calculate the base vector in different ranges. So we define the 3 ranges. So the first one is, of course, the gap in gray area, and then there's one interval that's left to the gap, and then there's one interval that's right to the gap, and right to the gap contains the peak of the posterior. So when we compare it to the usual convention, so it turns out that firstly, to highlight is the second row, the gap, the base factor of the gap is very small. It's smaller than the 0.01 convention. So that supports the constraint of this tiny gap. So meaning that our constraint is possibly real. And for the base factor of around the peak, which is just around 11.5, which is smaller than 100. So that means in terms of base factor scale, it's hard to conclude if a boson exists around the 10 to the minus 12 EV peak. And the reason is, again, we need many events to actually trace the critical spin curve to disentangle whether it's coming from an astrophysically small spin, and also or if the small spin is due to the superradiant spin down. So we need more events rather than just 45 events that we have now. So in the very last few minutes, I would go through some forecasts of our method and what's the prospect of our measurements. So, okay, so let's say we have a, if the 10 to the minus 12 EV boson really exists, so, how many more events do we really need in order to confirm the existence of that boson mass? The answer is many more, and it's about order of 1,000 events. So that maps to like probably a few years of LIGO vehicle or cargo detections. So, and also how does the underlying spin distribution at formation affect the inference? So, the whole thing wouldn't work, right, if the black holes were always born at very small spin. But the some hints from the GWTC2 shows that there's like a non-negligible fraction of black holes have non-zero spins. So you can read the race properties paper from the RVK collaboration, so I'm not going through the details. So I would try to address the first forecast first. And so to do this, we do a simulation study. So this is a BC plot, so I would just because of time limitation, I'll just focus the orange band here. So this is a base vector evolution plot. So the y-axis is the log 10 base vector, and then the x-axis is the number of detections. So the color band really tracks the accumulation of base vector as you stack more events. So notice that the x-axis of the number of detection in terms of total detection is on the order of 1,000. So that really means that we need in both two scenarios. So for left panel is the small spin distribution and formation, and then for right one is flat spin distribution and formation. In both cases, we need 1,000 events, at least a few thousand events to actually confirm a boson that is at the 10 to the minus 12 EV. And okay, and you can also ask, okay, so what is the importance for astrophysics? Like, okay, boson, I don't care about boson. So what's the importance of that? So it turns out that after all, we want to know the spin distribution at the formation, right? Because that's the astrophysical process that drives the spins. So we want to know their mechanism. But if we don't take into account of boson superradiance, we may be fooled by the apparently small spin distribution. And then we take that and maybe we model the astrophysical process incorrectly. So for example, in this plot, this is the posterior distribution of the spin distribution. So let's say we start with a formation spin that is uniform, so the solid black curve, and then let's say there's a boson that spins down the black hole, and then the actual spin that we can measure is the dashed curve, so it prefers a small spin. Let's say now in the inference, we don't include any boson. So we just say, okay, the formation spin is unaltered, and then we just do an inference. So it turns out we would preferentially try to match the merger spin after the superradiance, and then we will mistake this distribution as the formation spin distribution, which is not good because now, we will incorrectly model the actual physical process. Now we have to undo the superradiance effect so that we can have inferred distribution at the formation that is closer to the truth. So you can see the blue color band is closer to the uniform spin distribution. And I'll probably skip this slide. So this is another creative idea, I would say, that use multi-band measurement in future. So this is really future study. If you're interested, I can also talk about in the Q&A section. And for that, I will leave this probably one of the most important process in my life. So, and I will welcome any questions.
Thank you, Ken. Thank you for this very, very interesting talk. And we have a question from Richard.
Yeah, thanks. This is really interesting. Nice to see some of the particle physics here. So we also have very efficient astrophysical processes that can spin down black holes. So relative jets, for instance, can extract up to 30% of the rotational energy of a supermassive black hole. And I'm sure the uncertainties in the astrophysical spin downs are quite significant. So how do we know that the astrophysics or uncertainties aren't dominating the superradiant light boson driven spin down? And also, we can also have processes that spin up black holes possibly into the exclusion region. So how much of the astrophysical uncertainties count towards relative to counterbalancing the effect size of these bosons? And last question, there may also be coincident electromagnetic signals of coupling of these bosons to electromagnetism. So that could possibly be a way out of it.
Okay, wow, these are really wonderful questions, and I'm glad to ask. So for the first two questions, I can address. So in terms of basically it's a question, right? If I understand correctly. So actually, again, the Richard Brittle, one of the amazing experts in this field. So he actually studied the accretion effect on this superradiance evolution. So it turns out that in most of the case, the superradiance timescale is significantly shorter than the accretion timescale, even at the Eddington limits for stellar mass black holes, only for stellar mass black holes. So unless you have some formation scenarios, such as the active galaxy nucleus, say, I'm not expert of that, so I just mentioned this. If the black holes can accrete significantly, like, or even super Eddington over the super Eddington limit, then yeah, that may be a problem. But in current understanding is that the accretion of the stellar massive black holes binary is probably not that significant. So for our case, for LIGO black holes should be fine. But yes, for supermassive black holes, it could be a problem because now the accretion timescale can be comparable to the superradiance timescale. So if we want to do this using using the supermassive black holes, then the accretion physics will be very, very crucial. And I will point you to this reference. So that means when we interpret the spin measurements of the supermassive black holes, we cannot neglect any accretion physics. And you are right that that's very crucial.
Yeah, and the inflow properties are important, but also there are outflows and there's magnetic braking. There's also
yes. Sorry, continue. Yeah.
No, go ahead.
Yeah. So your third question, third. So about the electromagnetic radiation. So it depends on the coupling of the axion and also the in the electroweak sector, right? So from that, you may actually put a further constraint. So let's say you can model, say the coupling constant is strong, then we should expect there should be additional radiation photons that should reach in, let's say in the Event Horizon Telescope or things like that. Then yeah, so you can also further put limits on not also the boson mass, but also the coupling constant with in the EM sector. So that would be also very interesting, but I'm not an expert to that level. So yeah, that's what I know up to now. So do I answer this question well?
Yeah, thanks.
Thanks.
Other questions? So I have a question that I didn't fully understand at some point. You were talking about the, how more problematic is the inference of the superradiance if the spin distribution at formation is all low. At formation, you mean like before the superradiance is taken into account? So
Right.
basically that if they are all low at the beginning, it's hard to understand if the superradiance is having any effect on that.
Right.
Mm-hmm.
Yeah, so I can expand it further. So it's basically, so I don't have a plot there, so I should put it. Anyway, so imagine, let's say the spin distribution at formation is always, you know, they are initially clustered below chi smaller than 0.1. Then there's no chance for you to actually populate points along this critical spin curve. And then from the populational sense, then we cannot even measure any significance of the superradiance being done. So that's why we always stress that, you know, a simultaneous measurements of the spin at formation as also the boson mass is essential to do a model selection and try to see if boson existence is statistically conclusive or not. So yeah.
Okay, thanks. So any more questions for Ken? No, I don't see any. So let's thank Ken again for a very interesting talk.
Yeah, thanks for the invitation.
See you next week.
Yeah.
Thank you.
Thank you.